And I have one request to go at the beginning. I have one request to go at the end. We'll honor that. And then other than that, I'm just going to go through them pretty much in the order in which they show up in the GitHub org and work my way down through them. So if you want to get an idea of what's coming up next, just follow the list there. If I accidentally skip a file or something like that, we can go back and do it. Just kind of let me know. Worst case, we'll kind of do a catch-all at the end. Couple of favors I ask of everyone. One is, do keep your presentations short to 3 minutes. If you use less time, that's fantastic. If you use more time, then unfortunately I'm going to have to cut you off. And we didn't actually get a clock going here, but I'll give you like a 1 minute warning when you need to wrap up. And so please be respectful of that. Then to people who are in the audience listening, please do keep the volume down if you need to have a conversation, which I know, hey, it's a good opportunity to chat with people. Please just quietly make your way out so that you don't impact the people in the room, because it can be hard for all of us to hear. Other than that, enjoy the presentations. I hope they all go well. We are streaming them out on Meetecho. We're recording them, so they'll be there for later as well. Okay, with that, let's come up, kick off with quantum networking. That'll be our first one. You can just drive the slides from here.
Okay, thank you. So, hello everyone. So me and my team have been working on developing quantum networks. Since I guess it's a foreign concept for so many people here, I will have to answer what are quantum networks, why are we working in them, and how are we implementing them. So I'll start by the basics. In classical computing, I think the most basic element is a bit. It could be a 0 or a 1. But in quantum computers, it's a bit different. We don't have bits, we have something called qubits. And a qubit, unless it has been measured or operated on, it's going to be both 0 and 1 at the same time. I know it's confusing, but think about it like it's the Schrodinger cat. She's dead and alive at the same time. So it's very problematic when it comes to qubit because they can't be measured or copied. In classical bits, I simply copy it, inject it into the network, and transfer it over the internet. But for a qubit, if I copy it and inject it into the network, it will be downgraded to a normal bit. So it loses its special properties, and we can't use it for quantum computing anymore. So since we can't use the normal networks, the only way to transfer qubits from point A to point B is using something called teleportation. I know it might sound like a complex word, but we use something called quantum entanglement. So we entangle 2 points in space, A and B, together using this concept, and then you can teleport the qubit between them. So on long distances, some extra devices have to be used, which are quantum repeaters. So you can connect 2 quantum computers together in a distance of 100 kilometers. But more than that, you have to use quantum repeaters and create more complex entanglement to teleport the qubits. So the first real implementation of these concepts is going to happen in the Netherlands in 2020. So the plan is to connect 4 cities, the 4 cities which you can see on the screen. So hopefully this is going to be the first implementation of a quantum network, which really can transfer qubits between quantum computers. So it's still a very recent topic. And what we are working on in the IETF is, first of all, bringing some of the concept of classical networks to the quantum networks. I personally and 3 others have been working on adapting the concepts of routing and things that we currently use in the internet to fit for the quantum networks. Some of the colleagues over there have been working on developing a quantum ping, how to measure the quality of the quantum connection we're teleporting the qubits over, the specifications and requirements to establish a quantum ping. And 2 of us have been working on actually implementation of applications on quantum network, blockchain. So that would be my presentation. I think this is less than 3 minutes. So if anyone has any questions, I hope our theoretical physicist over there can answer them.
So next up, we'll do this one. I'm not sure what it is. Let me open it up. From MAP. Folks from MAP here, great. Let's just try to make this full screen for you. Should be able to, just advance these.
All right, thank you, Charles. I'm Dave Plonka. I'm one of the co-chairs of the Measurement and Analysis for Protocols Research Group. We're about 3 years old. We'll be meeting later this week. And this is the first time we had a hackathon table to focus on some live measurements that will give you some results in the meeting later this week. We did 3 projects at our table. I'm going to talk to you about the first one. For the last minute, Al's going to talk to you about the second one, and then we have a slide for the third. So what did we do? Well, we were interested in doing measurements that can inform the engineering efforts in the IETF and also inform the operations of those protocols. So if you're at MapRG, you're doing one of those things, bringing real measurement results that have something to do with the engineering or the operation of the protocols that the IETF defines. Our goal was to study, in this case, the privacy and security issues that we were seeing with IPv6 in deployments today. So when we're doing some measurement studies, the plan was to prepare an internet draft following the hackathon using the anonymized aggregate results that we prepared at the hackathon. So we're actually hacking measurement results instead of a protocol. And then the goal is to inform, as I said, the engineering and operation and practice of that protocol. What we're going to do here in the unique opportunity the hackathon let us do is take public data that my colleague Oliver Gasser from TU Munich is bringing from their project with Akamai internal things that we can't share to protect the privacy of clients that touch our platform. So we're going to get together here and find some way to compare apples to apples and bring a combined result that's hopefully more than either of us had on our own. So what we got done, we considered best current practice for the privacy and security of what we divulge in these results, and we realized that there are repositories of things like IPv6 addresses out there in the world today, and there might be best current practices that would prescribe how they should behave, whether they're commercial or public. And there's a URL here for Oliver's project and a couple of the tools that we hacked a little bit on today to get the combined results. So the idea was to take the 2 largest known IPv6 measurement surveys, public and private data, and combine them together. So what did we learn? We learned that as of this year, it's easy to call more than 1.2 million IPv6 router addresses that have UI64, meaning we know who manufactured them and we have their MAC addresses. This was discovered accidentally in topology and reachability studies, both done in academia and in industry. The interesting part is the public and private results don't overlap each other. They're complementary, so that's good and justified the use of the time here at the hackathon to compare these results. Another interesting result we had was older hit lists, ones for last year, actually produced more results than some of the new ones. So we're going to report the results, not here, but we'll show them after we think about them a little more on Thursday. And I'm going to turn it over to Al for the last minute to talk about his project.
Thanks, Dave. So I'm Al Morton, and I worked with Alexander on this IP network performance and capacity measurements comparison. Setting the stage for this is that internet access speeds are going up and into the gigabit range very soon for most of us. Some of us have these speeds now, and we've been looking at sort of ad hoc methods of measurement for IP capacity throughout the years, Ookla, speed test, and so forth. So we've decided to look at some new ways to measure this, and we've been looking at a couple of different platforms and opportunities. iPerf, of course, has always provided TCP measurements and UDP measurements. But we've got a new platform, basically a new tool that has a search algorithm built in that can do the UDP measurements very quickly. And so what we did was essentially create an additional test plan for looking at these test conditions. And then in the calibrated lab setup that we have, courtesy of Intel in Hillsboro, Oregon, we have a traffic shaper, and we're comparing each one of these methods of measurement to calibrated rates. And so far as we know, this hasn't actually been done where you set up a known value and then see what the measurements how close they get to it. Now, the TCP and UDP stuff from IPERF, they report out in the payload bandwidth, and the UDP-ST, that's the new tool, that reports at the IP layer, including the header. So they're actually getting close to the normalized values from 100 to 1 gigabit per second. And when you put in the correction factors, they all get a lot closer. But the key story is right here at the bottom, where basically TCP is kind of running out of gas at the 1 gigabit range in the 200. So we're cutting it off here, and that's a story you can come and hear more about later this week. Thanks.
So next up, the 6 tree. This is mostly paper bonds. I'll show you in just a second. Should just be able to use these.
And with this key, I go down.
Yep, it's down. It's full.
Hello, good afternoon. My name is Andreas Vogler. I'll tell you about our 6 tree project. It is the intention to have a very low latency routing protocol coming out of research projects in the microsecond range to support on the layer 2 the TSN, time sensitive networking. And so what we did is to have we cut everything to get it very fast. So no lookup, no prefix match, just self-routing. So take data out of the header and use it for routing. And of course also cut through technology. So the packet is forwarded before being completely stored. Just everything to keep it very fast. We used a crazy feedback from this meeting, crazy addressing. We mapped the telephone number into the prefix of the IPv6 address. It's all this. It sounds crazy, but already 20 years ago proposed by Korea Telecom Authority. We summarized everything in our internet draft. This is what we did here. So we had we bought real hardware because you need dedicated switches to do this. This research devices from outcome of research projects. What you see here is this on the display shows the IP address, which looks like a telephone number, and it is delegated to the next lower hierarchy level in the configuration time, and then it is ready for routing, hierarchical routing. What we learned here is very early technology, of course. We got valuable feedback thanks to the experts from Tony, from David and Alistair, that things to be considered. There is some, let's say, similarity with the Rift project. We had a long discussion, and we got the feedback to investigate behavior in case of failure, for example. What we also noticed, we are of course open to share the source code, but it doesn't help because the hardware is so expensive. So we have to think about that. That's one lesson learned. And to wrap up, so this is my name, Andreas Vogler, and Marianne Ulbricht is sitting here, my colleague, and we have one remote participant. And what we will try next is to forward the simulation, because this is cheaper, and also if possible emulation with a low-cost switch, at least for the behavior, and then can be accelerated in the real hardware. And for more information, if you click the link, you will find papers, articles, and so on. That concludes my presentation. Thank you.
You're up next. Hold on. Thank you.
I'll find out.
Good. to this one?
Yeah.
Retake.
Retake.
Should be good. Yep. Okay.
Hi, I'm here from the six-man group. We were working on PathM2 discovery. And so we were looking at a bit of a retake on how PathM2 discovery can work in the internet with IPv6. And we actually decided to do a re-implementation of a 30-year-old RFC, but this time on top of IPv6. This mechanism works unlike normal PathM2 discovery where you send stuff into the network and you get ICMP back. We add an option to IPv6 extension header. This extension header gets processed by routers and it works like a record route option. It records the lowest MTU on the path for routers. And the field goes to the end and then it gets reflected back somehow. And so the start of the hackathon, we redefined the option because we wanted to figure out a way to get the packets to be reflected. So the option format now looks like this, which is an update to the draft. We have two MTU fields. MTU1 is the MTU of the host sending out the packet to try and measure the path to see what's there. We have MTU2, which is a reflected field. We realized that we wanted to have a flag here, and so we compressed the MTU2 space, and so you can only have even number MTUs. I think that's okay. And so we get a respond request flag there. And so this allows us to have hosts actually actively ask for a response and just mark that something is a response. Yeah, and so what did we do? We had quite a busy table, or quite a few of us. And so we did an update to the draft just as a starting point, and then we worked on initial implementations for host for Linux and FreeBSD. We got two functioning router implementations in VPP and P4, and Bob, whose first hackathon it is, wrote a working dissector for Wireshark. And we've now interrupted and tested all of this, and it seems to work. And the script I have says that we have fixed the internet. What we didn't set out to do was do any performance testing. And obviously, this being a hop-by-hop option and being looked at every router on a path, performance implications would be interesting, and hopefully we'll be able to have time to look at that in the future. And we didn't try and hoop this up further into any operating systems. The host stacks we did were just looking at getting the packets generated and processing them and receiving them. And so, yeah, so this is good. We think this has been really, really positive, and it's managed to reinforce the work in the working group, and we think this is something we can carry forward. It's really reassuring to see that this could be implemented 4 times in like the space of a day and then interrupt and have it work. We don't know if it's deployable, no idea. And so we're going to continue looking at this. This says, look at IC, 6-man ICMP limits draft, so do that. Done.
If you do happen to finish in less than 3 minutes, you're welcome to entertain questions up here if you wanted to. Bit of a reward for finishing quickly. All right, so DTN.
Hello and welcome to our presentation. My name is Martin and I'm here to tell you about delay-tolerant networking in space. So what is delay-tolerant networking? Well, in current setup, usually when you communicate with a real computer, the other party has to be online. That's not the case with delay-tolerant networking because it's very difficult to achieve. For example, if you have a ground station and you would like to communicate with a satellite, there are all kinds of things which will prevent you to do so at the time you want to do that. For example, the earth between you and the satellite. So what we are doing actually is the preparation for DTN real space test, which is to be launched in 2020. In 2020, there's going to be a satellite, hopefully running micro PCN implementation of DTN protocol. And what we are trying to do and planning to do is that ground station 1 will measure some sensory data, for example, temperature. It will encode it into the bundle, and at some point there will be a line of sight with a satellite. They will learn about each other via beacons, and the ground station will transfer via bundle data measured to satellite. Then eventually, as the satellite continues on the orbit, it will see ground station 2, and again they will learn about each other via beacons, and they will transfer satellite to micro-PCN satellite micro-PCN implementation will transfer the data via a bundle to ground station 2. So that was our use case, and there are at least three drafts involved. There is bundle protocol version 7, then there is DTN TCP convergence layer protocol, and DTN IP neighbor discovery IPND. We found an issue as we were working on the demo. The IPND draft is expired, so since we need it for our testing to test our approach, the proposed solution is that we check whether it's still up to date, even if it's expired, and bring it back to life. That's our plan for Hackathon and also for the upcoming IETF week. So what got done? We got improvements on our PyDTN reference implementation. 19 issues has been fixed. We started PyDTN and micro-PCN discovery using IPND, and you can see a result of our work in GitLab PyDTN, link provided. We do have a feedback to, 1 minute? Okay. We do have a feedback to DTN workgroup, which is gonna happen, the session is gonna happen on Tuesday. And that feedback will be that we should bring IPND draft up to date because it's currently expired, and have it adapted by workgroup because we do need it for our testing. Then we found out that actually in IPND draft for the same thing, the different approach is used while encoding and decoding numeric values. So IPN is using SDNV, and the rest of the system is using CBOR2. This should be consistent, so we will propose to, as a part of draft update, we will propose to make it in line. Thank you for your attention. That's everything from my side. We are sitting right in the corner. If you have any questions, you're welcome.
Okay. Next up, EAP noob. Yep. Yep, backward. Thank you.
Good afternoon, everyone. My name is Aleksi, and I'm here to tell you about the goals and results of the EAP Noob Hackathon project. First of all, for those of you not familiar with EAP Noob, it's a new EAP method for bootstrapping devices with minimal limited user interface and no pre-configured credentials. So unlike other current EAP methods, we don't require any configuration, so you can think of any sort of new device that you just bought from the store and now want to bootstrap. The way this is done is using a user-assisted out-of-band channels, which consists of a step such as scanning a QR code or tapping an NFC tag. Over here you can see an overview of the EAP Noob architecture. So on the right-hand side, we have our new device. On the left, we have a server that we want to bootstrap it to. And in the middle, we have the in-band EAT network and the user-assisted out-of-band channel. There's currently an open source implementation available on GitHub, and it is a nice mixture of C code, Python, and Node.js on the server side, and C and Python on the client side. One of our main goals for this hackathon was to fork this project and create a version that reduces implementation dependencies and have it running as easily and quickly as possible. Out of the 5 exchanges in EEP-Noob, we managed to implement 2, and it's looking great for the rest of them as well. In addition to that, we discussed improving privacy by using randomized temporal identifiers, and we discussed with the authors about better compatibility with the EEP RFC 3748. In addition to myself, we had a great team consisting of IETF newcomers Eduardo and Anoop, and Alex, who joined us just for the hackathon. And every now and then, we also discussed and worked with the authors of the draft, Tuomas and Mohit. So if any of this sounded interesting, please read the draft, check out the implementation, and join us for EMU on Monday morning. Thank you.
Yeah, and thanks for that reminder to join the Hack Demo Happy Hour. Either present your project there or come and hear more about the projects that are being presented. Be great. I2NSF. Just download.
Hello, this is Jeon Poru-jung from Sungkyugan University in Korea. This hackathon for I2NSF project is ACE hackathon project. So this time we keep working for the validation of I2NSF, the major 3 interfaces, the consumer-facing interface and NSF-facing, and also the restoration interface. This time also we implemented translation stuff, especially policy provisioning using a machine learning scheme such as decision tree. So this is the building environment. So I2NSF is for a cloud-based security services system. So this time we're using Edge NFV framework. On top of Edge NFV framework, we implemented the IETF I2NSF working group framework. So basically, the user specify high-level policy into security controller. Security controller translate low-level policy rules for specific security VNF, virtual network function. So this time we implemented the translation, such as I2NSF user is administrator, specify security rule, and the high-level security policy delivered to security controller, and then using NSF database and translate the low-level policy delivered to NSF to enforce security policies. So this is the structure of policy translation. So we implemented the high-level policy specified sans PC cannot access some malicious website. And then that high-level policy can be translated into the IP address associated with the sans PC, and also website specified specific web URL. Also, we implemented using OpenStack SFC networking stuff, and then we implemented the service function training, such as a firewall and web filter using training. This time we proved concept, I2NSF framework, and also we implemented restoration interface, specifically that Yang, and also we implemented the translation based on NSF database management. Also, we are using SFC provided by OpenStack networking SFC. So we uploaded our code to GitHub. You can access tomorrow. Happy hour demo, we can demonstrate. Thank you for your attention.
All right, thank you.
And let's see, next up, IP Wave. That's you again.
So
you have them ordered consecutively.
Yeah. Okay. So yeah, so I2NSF project is a student project, and also IP Wave also student project. So my student working for I2NSF and I2 Wave together. That's why I'm present again. So IP Wave is for IP-based virtual networking stuff. This time we proved a concept of IP Wave OCB, and also we proposed the IP version 6 virtual neighbor discovery. So we proposed the IP version 6 neighbor discovery for IP-based virtual environment. So this is so this time two universities, my university SKKU and also Sungsil University, 2 professors and 3 students, also some other guests from other such as ETRI, and they participate in this project. So this is basically the virtual environment case. It is very hard to demonstrate the large scale. That's why we're using the simulator for, this is called the SUMO. SUMO is for mobility for vehicles. And also we using our protocol based on the OMNet++. OMNet++ is a network simulator providing PHY, MAC, IP, TCP stuff. So this time you can see 2 RSU and also 2 vehicles. Out of the coverage of RSU, we can provide the multi-hop DAD using our protocol. So we implemented the vehicle structure based on OMNet and also VANS. VANS is provided by some open source project. So it is implemented OCB. So from this project, we proved that the basic IP Wave IEEE 11 OCB-based IP version 6 delivery is feasible. Also, on top of it, we can implement the neighbor discovery, take advantage of the vehicle mobility. So we designed and implemented the IP Wave vehicle neighbor discovery based on OMNet and SUMO based. Also, next time we try to propose flexible mobility management for IP Wave. So this is appendix. So this is open source environment. Also, we uploaded the GitHub source code. You can test. Also, you can see the code. Tomorrow also happy hour hack demo. We demonstrate. This is a video clip. Thank you for your attention. Yeah.
Okay, so NTS, yeah, great. You good with that? Thanks.
Well, hello, I'm Martin, and this is a network time security team. Well, NTS, in a nutshell, it's a protocol to secure type information, in this case over specifically with NTP, the network time protocol. And the goal at this hackathon is the integration of NTS in different NTP implementations. NTS based on the current draft NTS version 17. It's in the pre-final state, and we guess we can release it soon. We're verifying the interoperability between different NTS implementations, and currently we have many of them. So we have about 5 working client and server implementations of NTS. We have also other implementations that are still in work in progress. And we have implemented in different languages. So we have C, C++, Golang, Python, and also we use different NTP implementations. So we have NTPD, NTPsec, Crony, and other NTP solutions. And the test covered 2 parts of NTS. So we have TLS-based key exchange. Afterwards, we have the NTP, authenticated NTP exchange. And the green parts in this table show the successful tests. So it looks pretty good. We have some outstanding tests, but we have no critical error. And yesterday we have some small bug fixes, and we have some small issues with OpenSSL. The last OpenSSL version have a bug in the TL exporter function, so we used a workaround for it. But in general, the interoperability test was pretty successful. We had no further problems in the specification, and we guess we can release it very soon. Yes, thanks to all team members. We are pretty many members this time. You see them, and you can join us, or you can join the Git repositories. Yeah, that's it. Thank you.
So DNS. Is there one presentation or is there multiple? Oh, cool. Yeah. Thanks. Maximize that. Should be able. Yeah.
Thank you. So this year I'm just calling our tables everything DNS because we did so much stuff. As usual with DNS, we didn't work on one major project. We had lots of things working in parallel. We had 5 bigger projects, 6 others going on, and lots of people. One of the big projects that we worked on was extended error codes. Don't you just hate it when you get a serve fail and you have no idea why? The idea of this is that you can extend the error codes in the response message and actually find out. The draft's been around for a couple of years, but the work that got done here was to implement it in 2 open source resolvers and works in progress on a 3rd. So that was all good. One of the other big projects we worked on was DNS cookies. Cookies themselves have been around for a while, but what's been recognized lately is there's interoperability problems between the different implementations of this in the open source code. A very recent draft came out, and what happened at the hackathon is that we now have 5 implementations interoperating with the fix to make them all interoperate correctly. Another project that got worked on here was DNS over quick, because we all need another transport for DNS, right? There's a draft that came out a couple of years ago proposing doing DNS over quick. There was some work at the time, but it stalled. What happened at this hackathon is there was a client implementation done in a performance tool called Flamethrower, and on the server side, a proxy was written to proxy the DNS from quick to UDP, and hey, it works. All good again. The last of the big projects is something we're calling ZOT, and that's because it's XFR over TLS. Who knew ZOT's a thing? That's the cute little guy there. Again, a very recent draft came out, and what we've done is there was work to support this was to improve a patch which enabled DOT in NSD, an authoritative name server. So we put OCSP in there. There's preliminary work on a chain extension, so that should be merged and released in the future. And in terms of the transfer, what we did is we got an opportunistic connection between NSD acting as a master and Unbound acting as a secondary, and actually got the data transfer working. So that's good, but what we've realized is that the authentication model behind this needs a bunch of work. And we also realized that this is a really nice candidate to take advantage of something new in the DNS called stateful operations. So we have the outline of a new draft about how to do this over stateful operations. Some of the other projects I don't have time to go into detail about. There's a Yang model for managing zones in the authoritative. There was additional work continuing to put DOE support into Stubby, work on a DNS tap multiplexer, work on a resolver testbed, work on dot in DNS Python, and work on zone MD in NetDNS. So all sorts of good stuff going on. This is our team list. Apologies, it is missing a few names. We did actually have 5 first-timers, so I'll fix this and upload the new slides. And that's everything DNS. Thank you.
There we go. You're too fast for me.
Good afternoon. This is a report of the OpenCheck project. So our plan here was to improve the open source implementation of Check. And Check, if you don't know, is the static context header compression protocol that's being developed at the LP1 working group. And the purpose of that protocol is to compress headers and do fragmentation and reassembly for extremely constrained networks with payloads typically of a few tens of bytes. So we intend to carry IPv6, UDP, co-op messages over those kind of networks. The current status is that we have a draft that describes the generic compression fragmentation engine that has been submitted to IESG for publication. So what got done is first we made the project more usable to newcomers by improving documentation, basic stuff, adding a README, cleaning up the repo, there was a dead code, adding a new wiki for more detailed explanations. We adjusted, the code is meant to run in Python 3 and also on MicroPython for microcontrollers, but it had mostly been developed on Python 3, and so we fixed the code so that it could run on, it can now run on MicroPython. We achieved that. We added tests. We added actually the PyTest infrastructure so we can run unit tests on all the modules. We added Sphinx documentation as well. And we improved the code base. We added more test content, and we improved the functionality, especially on the compression front, where the code was not fully implementing all the features of the draft so far. And also we added a connector that the code has a simulator of a link where we can set the loss rate for packets, but we added a connector so that you can use actual hardware and send your packets over a real LoRaWAN network. Oops, yeah, this is done. What we learned from the project is some parts of the spec were not clear enough. We had implementers telling us they didn't know how to implement that part because they hadn't understood it. So we'll add more examples to explain it better. And also we know the next draft that's coming up is describing the rule set that is used for compression and fragmentation and the context, the parameters, and this work allowed us to summarize all the information that you need to put in that context. And so this is useful for writing the next draft. And that's our team. There were 19 members, 3 newcomers, and 2 remote, one from Japan and the other one from France. And if you're interested, go to the GitHub project.
function did that. All right. Spin dump. Do we have the presenter for spin dump? Okay, coming up. No? Do we have a... Oh, you're the presenter. Okay, great.
Hi, I'm Marcus Hiller. We have been working on measurement of quick using the tool we have designed called spin dump. So we have developed this tool for doing in-network performance monitoring based on some new mechanisms for quick called the spin bit. There are some drafts you can read if you're interested in it, the Trammel IPPM spin and so on. So what we've been trying to do this hackathon is to improve this spin dump analyzer tool that we've implemented. We tried to implement some aggregation of several instances of these measurement tools and try to visualize it, basically. So what did we get done this time? We added some more support for some more quick versions, like old Google quick versions and the new IETF draft 18 version. We updated some some reporting formats, JSON-based, fixed a lot of bugs, and we've been started to work on an aggregation server that takes data from multiple spin dump instances and collects them and provides some nice statistics. We're also working on a tool to visualize this, that sort of we're combining measurements from different points in the network, and then we can show performance-related things from different segments of a network. And then we have been discussing quite a lot with different people doing measurements and proposed measurements of encrypted transport protocols. So we have been looking at some new mechanisms for measuring packet loss and improving latency measurements and so on. And there's some really interesting work there being done by Mauro and others. And that might be a future candidate for this spin dump tool that we're working on. And moving on from here is that we are preparing a demo for this hack demo event for tomorrow, where we will be visualizing our data. So we will have a set of these spin dump instances associated with a bunch of routers, and then we can display end-to-end and segment-based performance monitoring. So please come check it out. And yeah, that's basically it. If you're interested in this kind of stuff, you can check out our work on GitHub. It's available there. And the team members were Jari Arko, Sylvester, me, Ronnie, and Mauro, as well as Zahed down there. I forgot you.
So suit, all right. Okay, I'm happy with that format.
Hi, so I'm going to talk about what we did in Suit. So for those who don't know, Suit is working on an architecture and metadata format, standardizing this type of stuff for IoT firmware updates, and do that in such a way that it also applies to the full spectrum of IoT, not just Raspberry Pi type of stuff, but also smaller stuff like microcontrollers that are much more constrained in terms of resources. In this hackathon, we focused our work on implementing the latest version of the metadata draft. So this draft, which I indicated here, which actually specifies a CBOR-based format for the metadata of such IoT firmware updates. So what happened at the hackathon? we actually have now two independent implementations of a generator for this metadata, one from ARM, one from Renesas. We also have new parsers, so we have three independent implementations of parsers, two of which are actually running on actual IoT devices, so small microcontrollers of between class 1 and class 0, and class 1 and class 2 types of devices. We have interoperability between the manifest generator from ARM and two of the parsers that we have, so from INRIA and from Renesas. And we also demonstrated a full workflow that we want to enable with Suit architecture, so where you actually can build a firmware, actually generate the metadata according to the format, and actually transport all of that through a repository to the IoT device, which is then able to verify and then update the firmware. And we did that on top of Riot running on these devices. Now we see one of the devices that we used. Perfect. This is the team. We were 12 people. We had lots of fun, and we actually achieved quite a lot, I think, in this this hackathon with interoperability and the full workflow. I think the main thing we learned was that it's really important to just specify one way of doing things in the spec. Else it's just like, well, can of worms. And so we're pretty happy. If you want more info about Suit, go to the website of Suit, and also just check out this draft. And we also have an Etherpad where we noted most of the things we did. So thanks. That's it.
Next up, let's see, where are we? T. Fantastic.
Yep. All right, so at first I wasn't quite sure how much we were going to get done at the hackathon until I saw this sign here, which told me how much we were going to get done. A ton. So our group was Trusted Execution Environment Provisioning, and so this is the TEEP working group, which tries to figure out how to provision code and configuration into trusted execution environments such as secure elements, Intel SGX, TrustZone, and so forth. This was our third hackathon, and so our plan was, since the drafts are still in progress, to try to flesh out implementation details. And one of those drafts, the actual protocol one in the middle there, is sort of known to be underspecified. And so we were trying to figure out what are the areas of ambiguity as we tried to implement things. And so we tried to compare our implementations and to validate that that spec is actually agnostic as to which type of TEE that it's intended to work with. We had representatives from 2 independent implementations present. And across those implementations, at least 3 different types of TEEs were being covered. The participants were using an open source SDK called Open Enclave, which provides an abstraction over the type of TEE that we could build the protocol on top of. That was new for this particular hackathon. One of the 2 implementations is open source on GitHub that's there. And so for that one, it was ported to run over that SDK. Last hackathon, it was just SGX only, and now it's agnostic to run over TrustZone as well. We added some more of the spec, made more progress there. We updated to match that third spec, which didn't exist last IETF, which was how do you write, what protocol you use as the transport for OTRP, and it's using HTTP. We kind of designed it on the fly last hackathon, and so then it was written up in a spec last hackathon, and it was implemented this time. And we updated it to match recent feedback from people like Mark Nottingham. And we implemented another mechanism that was designed in the middle of last hackathon that hasn't made it into the spec yet. It's just documented in GitHub. So design in progress. We filed a number of new issues. They're tracked in the GitHub on the issue tracker for the draft. And there's a summary of the issues which we will talk about in the OTRP working group. For people that are not in that working group, if you're in an attestation working group, one of the issues has to do with the relationship between the OTRP protocol and attestations, such as being done in the, say, EAT or RATS proposals and so on. So the relationship between those, and that is on the agenda for this working group meeting coming up. And so there's our team. Last hackathon, I reported that our team size had doubled from 1 to 2, and this time it doubled again, so we're making great progress. 2 of them are first-timers, and so there we go. That's it. Thanks.
ACVP.
All right. Hello, everybody. I'm Chris Seeley, and here to talk about ACVP. So briefly, ACVP is a JSON transport protocol over HTTPS. The goal is to provide a standard protocol and data model for verification that crypto algorithm implementations are correct. And we provide an extensible data model to cover testing of new algorithms as they get released. So the goal of the protocol is to come up with a common protocol to enable technology providers to interoperate with multiple validation authorities. This may be FIPS 140-2 or common criteria, or even non-government related authorities. So the plan for the hackathon for us was to implement AES GCM SIV as an extension on the server and client based on a draft specification that we had written for AES GCM SIV on GitHub. Here are some of our various drafts. Right now, they're just internet drafts. What got done is we completed fully everything that we had set out for. AES GCM SIV is implemented on both the server and client. The current data model as well was extended to allow for GCM SIV testing. Interoperability between the demo server and the client was fully completed and successful. The server now has an AES GCM SIV implementation to support the generation and validation of test vectors. And the client uses Boring SSL's GCM SIV implementation integrated with Cisco's open source client to actually run the test vectors. So what we learned, we now have a protocol that can remain unchanged while accommodating extensions as new algorithms, and we're interested in forming an ACVP working group in the future. So a quick wrap up. Everybody on our team was a first-time member here. We have a side meeting that should be on Tuesday. So if you're interested in this space, please come join us. We want to put together a BOF in Montreal at IoT 105. And as well, we have a mailing list to join if you're interested as well, acvp@ietf.org. So thank you.
Okay. So the topic of the project we worked is a problem in testing and simulating networks. This is taken from one of the oldest and most common drafts, RFCs from the benchmarking methodology work group. And it is probably, as you can see, very simple to understand what the project was about. Now, in today's world, there is a lot of progress in creating models and writing young models and implementations which represent the device under test in this situation. But what is missing is a model of a host, or as in this case, a tester. So the problem with that, obviously, is that you don't have a model-defined network if you have part of it, which is very important, which you cannot model. Like in the case today, you have to run a ping, which is an application which will send data and will simulate some traffic. Or you can run an iPerf. But there is something that can be done and has been done in simulation world, like PSpice. There you have models for sources and sinks. There is also simulation primitives in VHDL, which simulate source and sinks so that people can write tests. And this has been existing for a while in the network simulation environment, like tools like Omnet PP. They have their software-defined networking concept from 10 years ago. So they were able to reproduce a topology with all the packets being generated, received, and do that in a model. So today we have in target, in real networks, the device under test. This is the real networks which actually have young models. So that what we are working on is creating a model for controlling a traffic generator. So the problem is today you have to buy a traffic generator which is proprietary. It is not interoperable, and if you create a test case for it, you can't really simulate it. So you really have to have the expensive hardware at hand so you can test it. And if you have a simulation, you cannot just take that simulation and reuse it in the pattern that will be generating the test. So we want to go from software-defined networking to model-defined networking, and by using that concept, we mean that also the data plane can be modeled. That way you don't have a software tools like the ping application and the iPerf that you need, but you can specify exactly how the traffic generated will look like in the endpoints. And we have a draft which is based on what we think is possible today. These are some details, excerpts from the draft. So this is to take the traffic generator, because there are three components. These are some of the leaves you can configure. And when you configure that and you commit your configuration, then the generator will start generating a waveform. Yeah. So if you see this commit at the end, it's very important. It has to be simple, because hardware people also have to use this API. And there is a test case which we use to demonstrate how it's using the draft. And then one thing that is very easy with the model of a traffic generator is that you can actually write a test script that is universally validating devices that implement it. The advantage is that you can create a loopback, you can create a traffic, and you can check the status in the analyzer bit. And then you can easily validate if the traffic generators that you have in your network actually generate what they are supposed to generate without writing a single line of code. So this test case we committed as part of the work on the project. And now I want to give word to a specialist from the simulation environment, which sees also advantages in using such a model in their development.
Hello everyone, I am Attila Török. It seems like I have 5 seconds per slide, so I'll just flip through all of them. The sub-project I've been working on is a software simulation-based implementation of these models. Some of them are standard IETF models, some of them are Vladimir's drafts. And the major part of it is a tiny Python script that loads an XML representation of the whole network and the configuration of the hosts, and that conforms to these models and generates different NAD syntax files. Basically, it's the same information, just with a different format. And when it's executed, it looks like this. This is one of the example scenarios. You can see the insides of one of the hosts and the switches and the queuing inside one of the interfaces. And I think simulating these kinds of things is great because it makes experimenting with new concepts easier and faster. And we also made a teeny tiny new Yang model, but that's not that important right now. These are our names. By the way, it was my first time at any IETF related event, and you can find the links on the work we did here.
All right, C4. All right, you can just advance.
Hello, I'm Matsuno. So let me talk about this CEPHOR project briefly. So this activity is related to the ICN research group because CEPHOR is open source software enabling content-centric networking CCN communication, which is available at this website. And the objective of this project is to enhance CEPHOR functions, such as extensive forwarding engine, which is compatible with CCNX message, which defined in this draft, and in-network caching management, and so on. So we have 3 goals in this hackathon. One is to implementing CCN info, which can be used discover information about network topology and in-network cache. The specification is described in this draft. And the second is developing transport program for network coding in coordination with in-network caching in order to achieve high performance. The requirements is described in this draft. And third is to implement CEPHPICO, which is a Python package to enable faster and easier CEPHOR application tools. So as our achievement, we built the basic function and the framework, and we enhanced the CEPHPICO to specify the optional TLV header flexibly. And testing will be a huge work. This is our team members, and we add CEPHOR links. So if you have any question, please ask us. Thank you.
So for dots, yeah.
Hi, I'm Kanami Nishizuka from NTT Communications. My presentation is about DOTS interop from DOTS working group. I have made a presentation several times in IETF hackathon. So however, you may not know about what DOTS is. Then DOTS is the DDoS open threat signaling. So it standardizes the signaling for DDoS protection between 2 or more organizations. DOTS protocol consists of two drafts. One is a signal channel draft, and the second one is a data channel draft. However, on top of that, we tested a new individual draft, which is the outcome of the last IETF hackathon. Then we did the interoperability testing between two individual implementations. One is open source, and the other end is proprietary. Then we made a demo of several use cases. Then here's what we get done. So here's a matrix of the result of interoperability testing. Then we have the over 90% of test coverage. Then also you may notice that orange cells are what we did in this hackathon. Then we tested new features of filtering control of a signal channel, even in attack time. Then, as I said, DDoS DOTS is about DDoS protection requests from one organization to another organization. So when one organization is get attacked, then they ask for help to other organization. However, in current specification over the DOTS data channel, there is no chance to convey the control of ACLs in other organizations, mainly because data channel is over TCP. So our solution is using the signal channel, which has a more compact wire format. So then we can enable the switch on and off of the ACLs already implemented in the other end of DOTS protocol. Then here's what we learned. So the DOTS protocol enables the mitigation request and ACL control even under the hostile network situations. Then issues found in IETF 103 hackathon were all addressed by the effort of working group members. Then we will feedback the implementation considerations to the working group. So here's the team members, and it is remarkable that we have included 4 new members, and they contributed to the OSS project. Thank you so much.
Okay. DSCP. Folks from the DSCP team. DSCP LE. Oh. Is this one of the ones being presented at the end? Logan, are you there? I can do it at the end. I didn't realize you had more than one. Okay, we'll save that for the end. I think that was from our remote, one of our remote presenters. So let me find the next one. How about this one? IETF mobile app. Anyone here from the IETF mobile app team to present? Okay, I'm on a bad streak here. And where were we? How about taps? Great, thank you. Just advance. Yeah. Should wait one second. Should work.
Hello, I'm Teresa and I'll present TAPS. TAPS is for transport services, and the idea is that we're providing an abstract API or a common abstraction on top of different transport protocols. And then, for example, an application specifies some services, some transport services it needs. For example, it needs reliable in-order data transfer, and the transport system underneath will figure out, for example, whether to use TLS over TCP or whether to use Quake. Or there can also be other transport services that are supported in other transport protocols. Our drafts are still work in progress, so we wanted to get some more implementation experience. And we worked on a new implementation of TAPS called PyTAPS, which we had written from scratch based on Python async IO. And at the beginning of this hackathon, PyTAPS only supported TCP, and TLS, UDP, Quake, and STTP were planned to support, so we wanted to see how far we can get within the hackathon. Now TLS 1.3 works with our implementation, but this is thanks to Python async IO and the underlying OpenSSL library that actually, so we just provide a security context with some parameters, and we get sensible defaults, and then TLS works, so we can now use TCP and TLS within our API, and UDP is work in progress. There's code, it's not merged yet, but we're still working on it. And we have an idea how it might work to integrate Quake into our prototype, which is quite exciting. And for SCDP, we haven't had the chance to actually integrate it yet. So what we learned is that finding the right abstraction is non-trivial. APIs are hard, right? And even within Python async IO, we started out with a more high-level abstraction that worked well for TCP and for TLS over TCP, but then we had to eventually basically go down a layer within async IO, and now we're implementing the protocols on top of the base protocol abstraction, what we call it. So if the protocol is implemented using async IO, we think that now it will be possible to integrate all those transport protocols into our prototype. Let's see what we can do about protocols where this is not so easy or this is not the case. We will take our implementation experiences back to the TAPS working group. So team members are myself and Philip and Max. We're all at TU Berlin, and our table is right at the front. So if you have any questions about TAPS, you can look at our GitHub, you can write us an email. By the way, we're all first timers at the IETF Hackathon, had a great time, it was very useful, so might be back. Thanks.
Template, okay. 451. Oh, I see. That's one to save for the end too. Okay, Rift.
Okay, 1.5 hours, first cool picture of the day, now. We should already win for that. So this gentleman is not a participant, had an important role though. What were we doing? We were doing chaos monkey testing on a routing protocol, which is probably like the first that I've seen. What is Rift? That's a specialized protocol for special data center topologies, metro, building cabling, which is becoming more and more important. There were 4 people hacking code and tons of groupies we don't mention, we don't count them. We have an open source implementation. So one of the implementations is actually open source on GitHub. We generate a configuration of large data center topologies, actually not that large. Ran the whole thing in AWS, everybody's in the cloud. We did a lot of testing of correct initial convergence, and then we monkey chaos tested the stuff, which means we were just breaking things as they came. More
there was a lot of preparation, so we already came with the framework to bring all these things up. I mean, there's not much time here. Material is out there, including like videos and so on. So that's all generated out. We have a lot of cool pictures. So the tool generates, shows the topologies, what's coming up, what's breaking, and so on, different resolutions, a lot of SVG stuff. So we run the whole thing in network namespaces. I think we started with containers. They were far more tedious to get the stuff done. We had some kind of a meta configuration, which actually generates a YAML configuration, which runs the whole thing. So it generates configuration per router, all kind of scripts to start, stop. I mean, you're in namespaces and you have, dozens of those nodes. So this is non-trivial how you operate on such a topology. Then we had, the chaos scripts that were perturbing the thing. And then, of course, a lot of checking, right? Because you have a lot of levels. Did the protocol converge? Do you have the stuff tie broken? Do you have in the kernel? Does it ping from here to there and so on? Right, so we generate this chaos script, we run the stuff, we break links, we break nodes, we will add packet drops, reordering packet, corruption and so on. All right, so that's a typical run. Some state, you break a couple of things, you fix a couple of things, interesting stuff. So what did we test? Like pinging from all the leaves to all the leaves, whether nodes are up, adjacencies are up, whether all kind of routes are installed through all the levels necessary to actually make forwarding work. More ideas are there. Again, lots of cool pictures. So this is some protocol run where you can SVG look at all the packets flying between all the nodes and actually analyze, what's coming up, what isn't. So what did we do? Generate those topologies, run them, flapped it. What did we learn? We found a couple of implementation issues, very delicate stuff, as it mostly comes from chaos monkey testing, based on timing stuff. No protocol specifications issue, but simple implementation. So, for example, we have v4 and v6 support, and we found that when one node was flooding on IPv4 in one direction, the other in IPv6, there were some timing issues. Exception shutdown scenarios, right, when things comes up and down, unexpected sequences, and basically added a lot of infrastructure to just validate that we get an expected state, right? Look a lot of routes and so on. I think that's it. Yeah. Yep.
Thank you. List is getting too long. Huh? Too many files. Yeah.
All right. Hi, I'm Jake Holland, and it was a surprise to me to be asked to present for DNSSD because I did not actually work on the DNSSD implementation. I am instead a user of DNSSD who had a problem that could be well solved by that. So they asked me to go through my use case, how DNSSD solves it, and my experience with the library. So my use case is this. I'm running multicast into a home network. And the idea here is that you've got a multicast capable network that you're within. And the Wi-Fi can't support multicast because it's broadcasting Wi-Fi. There's a draft about it. It's kind of a pain. So what we do is discover the relay, and the relay can wrap the multicast data into a unicast tunnel. So we discover the relay, pass the join through the relay. The join propagates into the multicast-enabled network, and the data is received by the client. So the bigger context of this is that I brought this all these devices. There's a multicast network which is ingesting traffic from the internet with the same idea, with a unicast encapsulated tunnel, and then propagating the multicast as native multicast within the network. So it's very important that the home device doesn't reach out to the internet when there is a nearby multicast-enabled network, and instead finds the local relay when it's there. If it's not there, then it should reach out to the internet to collect the data. So that's my basic idea. And there's 3 relevant documents that were addressed as part of this work. The DNS service discovery, of course, is RC 6763, and it's got great mature libraries that work very well. Docs could maybe use a little bit of work, guys, but with Stuart there to walk me through it, it was fantastic. And the draft about the discovering over the internet the unicast tunnel for multicast source. There's an update that I'm going to apply to the draft based on some things that I learned during the hackathon about how the discovery is going to work, and also some interesting information for the MBOND group about a proof of concept for the draft about the Wi-Fi multicast problems that the AMT running on the local network, on the home network, is one of the cited workarounds, and so it's a proof of concept that this is a viable idea. So that's it. Thanks a lot to the DNS team for DNS SD team for inviting me to join them, and for giving me the opportunity to present, helping me get it all working.
All right. ILNP. Oh, you're right there. Great. I looked back there. You weren't there anymore. Like, uh-oh. All right. Does this presenter view thing work for you?
Yeah. Great, thanks. Hello there. Rio and I are here from the University of St Andrews. We've been working on an implementation of the Identifier Locator Network Protocol, which we've been debugging and testing and will be released in May. Thanks to Arstor for helping us be here and have our demo kit. Just a little bit of background on ILNP. It's a change to the way that addressing works for IP. So this is what we might see today. We have a Linux box and we see that an interface has an IP address attached to it. If we look at that in the context of the protocol stack, we see the IP address gets used in several places in the stack, and each time it has a different semantic. And also we have some binding issues potentially, for example, because the IP address is bound to an interface, but it also forms part of the state for the transport level identity, the tuple. That means effectively a transport session is bound to an interface, which can be a little bit inconvenient if you want mobility or if you want multipath or multi-homing. So in ILNP, we try to change the way that addressing is done. We introduce new namespaces. So there's a specific identifier at the transport layer that's only used end-to-end, and there's another namespace, a locator, at the network layer that's used just for routing. And then we have dynamic bindings between them. So a node identifier can be dynamically bound to one or more locators, and a locator can be dynamically bound to an interface. And by playing around with those, you can get different things like multi-homing and mobility, and a mixture of those things if you want to. This is just a summary of the properties of the new namespace, and the details are in RFC 6740 to 48, which are experimental, and also these form the basis of the spec on which we're building and testing the implementation in Linux. In terms of getting this onto the network, we want to ship those locator and identifier values across the network, so we build ILNP as a superset of IPv6. And so what we do is we take the address bits that are in the IPv6 packet, and we reallocate those to carrying locators and identifiers. And as luck would have it, a locator can be an IPv6 routing prefix. So it has the same syntax and semantics as an IPv6 routing prefix, which means IPv6 routers should just treat an ILNP packet as an IPv6 packet. And then the node identifier, which is the lowest 64 bits of the 128-bit IPv6 address space, that is used at the end system, so the end system stack has to be updated to recognize this split and to deal with the new semantics. So we have a demo, and it will be showing how mobility and multi-homing can be achieved together by binding a node to multiple networks through the dynamic binding between a NID and an L64 value. And we have mobility by having a node move between networks. So this is the little mini testbed we have, which is currently at the back and it's been torn down, but will be at the hack demo session tomorrow. And the blue nodes, the correspondent node and the mobile node, are ILNP enabled, and they're communicating across a set of routers that are IPv6 only. They don't know about ILNP at all. But what's happening is that the mobile node is moving across those networks. We emulate that by taking interfaces up and down. And at the same time, there's a flow running using IPerf between the CN and the MN. And we show what happens, that the flow remains fairly stable, the communication continues. And the IPerf happens to be an IPv6 binary. It hasn't been recompiled for ILNP. Okay, the graph didn't come up. You'll just have to come to the demo tomorrow to see what happens. And as I said, we are at the demo tomorrow, and more information about ILNP is available at the website, and that's also going to have the link to the code release in Linux in May. Thank you very much.
IPv6 flag only. Oh, wow, okay. Okay, how about this one? Great, thanks. All right, so just kind of get that full screen. All right, should be able to advance.
Hi, so we made a hackathon for the low loss, low latency, scalable throughput architecture. And so this is mainly against fighting the SOTIF that you observe at your bottleneck links when you have capacity-seeking TCP flows. So why is that bad? Well, basically it builds up queues, and so it increases delay. And so if you want to do, for example, AR/VR workloads, it doesn't work. So this has been an effort that started a couple of years ago in a European research project. And it basically started from DCTCP, which enables you to precisely control the sending rate, the congestion windows at your senders, such that you don't build up queues. From there, actually last year, RFC 8311 came out, which relaxed the ECN meaning, so we could experiment with it. And then there's a bunch of drafts that leverage all of this to define an architecture, how to communicate ECN feedback to senders, how to build up an AQM that does this and stays fair with other TCP flows. And then there's a final draft that discusses what we call the TCP prior requirements, which were specified here 4 years ago. And that's a bit the sad state of the story. So DCTCP has been in Linux for almost forever now. The RFC 8311 is there, so that's nice. The architecture has mostly not evolved for a while, and so this is static. This is well known and understood. AQTCN has been prototyped in an older version of Linux. The AQM was released publicly in July 2016. and well, the requirements are text. So what did we do for the hackathon from there? So we wanted to take all these building blocks and get to a point where we had an environment so that open source people could experiment with it, not only behind closed doors. So we got a bunch of scripts to set up a VM, build up the custom kernel and extensions with sample labs that showcase how to use it if you want to use TCP Prague or DCTCP or something else. We've updated IETF to the latest revision of the draft and stumbled across a couple of issues with the generic receive offload and segmentation offload, which are extremely important if you want to get high performance. We started working on the implementation of the requirements for TCP, and we actually have a small prototype for Quick that is compliant with L4S. So that showcases how generic it is. So as I said before, IETF is a small modification to the TCP wire protocol, and so it modifies bits in the headers, and it turns out that the meaning of those bits is goes extremely deep in the stack. So we had to make fixes in the lower level of the kernel, and we actually expect hardware to have some issue with it. Not all Prague requirements might be needed, and the easiest part of this is, well, for Quick, for example, you have an embedded ECN feedback counters that's propagated in the DAC frame. So implementing it for Quick is way easier. And finally, once you get low latency, well, you can, for example, for Quick, start to do smart things with the built-in streams. So there were 5 of us here from different places. We pushed most of the code on GitHub, scripts to build a VM, kernel changes, AQM, some test code that might need to be cleaned up a bit. And then there's the right project for the usual reference. That's it.
Okay, OpenWSN. Thank you.
So there's one for me.
Oh, yeah, this one.
Yeah.
Okay, just forward.
All right, thank you. Hi everyone, I'm Teng Fei Chang. I'm from area Paris, and I was coming here with my colleague Malaysia and working for the OpenWSN project. So our target during the hackathon is evaluating the performance of SigTish. So for someone who don't know SigTish, SigTish is a protocol stack. It's running on the low power wireless constrained device, which is used in the industrial scenario. And the up layer is running a IPv6 stack trying to connect to the internet. So SigTish is a active working group, and it already published several RFCs, like RFC 8180 and 8480, and also several drafts that we are right now is trying to evaluate the performance. One of them is the SigTish MSF draft, which is a scaling function running at the MAC layer. So in another target during the hackathon is we're trying to benchmark the SigTish performance using a continuous delivers platform. So what do we plan to do? First, to implement the MS draft, we are using OpenWSN project. OpenWSN is an open source implementation of SigTish, and it has already implemented the whole SigTish stack. So we use this stack to replace the MAC layer by the latest MS draft. And for the benchmark projects is open source as well. And it contains 2 parts. The front end, it's a web interface which can manage the experiments, such as start experiments or terminate, and backend to integrate with the mode over testbed to get the KPI performance. So this is how we started yesterday, And this is our table looks like. And this is my college manager is working hard there. So after this 2 days hackathon, what we got is the MS version 02 is implemented. And for the benchmark, we created a co-op application, and it can interact with the benchmark service and trying to communicate with the mode, which is getting the data from the mode which is running the SIGTISH implementation. And our code is available in the link, and we have a live demo on this link. If you open the link, it will look like this. And on the first chart is the end-to-end average latency. And the second one is the end-to-end reliability. And the third one is the cell massive cell usage, which is an indicator for the traffic load in the network. And for our, so it probably looks different if you open the link right now, but which is fun. So we are really more targeting the reliability rather than latency. Yeah, this was SIGTISH targeting. So what we learned is we found that the latest MSF draft version is better than the previous one in 3 aspects: network forming time and the cell location efficiency, and the reliability is also increased. And we also found a problem with the synchronization takes long. That's because channel hopping features. We are continuing working on this. So if you're interested, we are in the third tables from the door in the middle. So feel free to come to talk with us. That's it.
You're next. Okay, which one's yours? This one right here? Yep, perfect. Yeah, or I think this would work too. Yep.
Hey there, everyone. My name is Ken, and I'm going to talk about integration of SIGTISH, which Tengfei was just talking about. Thanks for that, with the Riot operating system. So our specific goal was to tighten the integration of OpenWSN as an implementation, the reference implementation, into Riot on some useful hardware. And so this is occasional work for us. We had some restarting work from earlier sprints, but valuable nonetheless. In particular, we're trying to get it to run on OpenMoteB hardware, which is the reference platform. That also eventually will get us to 15.4G and long range. And also to improve the integration at layer 4 so that we can run our applications on top of it. So let me explain that a little bit better. So on the left, you can see how things are fit together. On the top, part of the work was the integration with the SOC API, the third one down, so we can use CoAP on top of that to be able to test our application. And then down on the bottom layer is the other part that we're working on, which is the network device API, which is relatively abstract, and we had to integrate that in better. And you can see over on the right side the sort of issues that we're dealing with in terms of timers, which are critical for OpenWSN and SIGTISH, as well as the communication with the radio over the UART. So what we've been able to do on the top end is to use the FIT IoT lab, which is very convenient for us to be able to just run experiments. And so you can see here on this Wireshark output, we have the CoAP output, a CoAP request and response, as well as the frames. So we kind of sort of had this working in the run-up to the IETF, but we were able to confirm that things were working. So this is very good. And so in terms of top-down results from working at the SOC API layer, and one thing I should also say about the SOC API is that already it's implemented for Riot's native stack, as well as lightweight IP and EMV6. So it's really cool that we were able to graft into OpenWSN to be able to work with it at that level. So I was able to rebase the work that I'd done and resolve some compiler issues and prove that things are still working on the IoT lab modes. So this will be valuable to us in the future. And also it was great for me. I live far away from most of the other contributors, so to have some face-to-face time was great. In terms of bottom-up results, we've discovered, so this is running on TI hardware, that we need to learn more about TI hardware. And so we start from an abstract interface. We're trying to understand the data sheets. So working with the timer and the radio APIs proved to us that we have more work to do. We need to improve the quality of the driver. So not as positive as we might hope, but still there's a lot to be said for learning in the face-to-face time. So just to wrap it up, here's the 4 members of the group, and we do have some work in progress PRs that you can take a look at on the Riot website.
Okay. Hey, I know Alex has a presentation he wants to get uploaded to the GitHub repo. I don't want to do that right now because I'm driving with my laptop here. If someone who has access can raise your hand and help Alex, he's in red shirt back there, that'd be great. I would appreciate it. And let's get yours. You're this one, SRD6? No. Oh, this one, yeah, thanks. I'm getting lost. That sounds good. Should be able to use it.
Hello, everyone. I'm Hauke, and me and Schenk, we have been working on Ripple over BLE during the last 30-some hours. So our motivation was a little bit looking into Bluetooth Low Energy and the integration with the internet. There is, of course, some standardization from the Bluetooth SIG and also from their IETF. But one of the problems we see is there's no standardization on the connection handling in Bluetooth, which means the IP over BLE is based on Bluetooth connections. So devices have to peer with each other, kind of. Also, they call it differently, I think. But there's no really standardization on when to connect to whom. And one limiting factor, especially when talking about these very constrained devices, is that they, of course, are limited in the number of open connections they can maintain. For one, because of the timing parameters, but also because of the memory they need to spare for these kind of connections. So there's 2 existing work that we know of and we based our work on, basically. The one is the draft and the 6-law working group. And another one is a paper where also people already did kind of Ripple over BLE. And so our plan for the summit, for the hackathon, was to take both approaches and take the best ideas that we found and try to just make a quick prototype and see how far we get. So the concept is quite simple. Bluetooth also on the side offers this broadcast domain where Bluetooth nodes send advertising data to each other that can be scanned. And so all we did is take some Ripple metadata information like rank and codec ID and so on and implement it or put it into this advertisement data. So nodes can actually, based on the advertisement data they receive, can do decisions on who to connect to. In our case, we decided to have the strategy that nodes simply decide their parent, so they only connect to their parent actively. So our results, we got a more or less stable solution on our table there with 6 nodes, and we configured them in a way that they only accept one connection. So we basically have a line topology with a 6-hop thing. It was stable for 10 seconds maybe. During this talk, or all the talks, we improved performance by about 600%. So we are at a minute right now. And yeah, so all that's left is a lot of debugging. What we learned, the general concept is actually quite straightforward and simple. It's look for advertisement data, do some metric calculation, and do a connection decision. Of course, there's some problems we encountered. And for one is the NimbleNet Bluetooth stack that we use. Basically, we have multi-layered state machines because you have the general connection between nodes, and then you open to A2CAP channels, and on top of that, you basically have the IP traffic. And so to synchronize all these state machines, there seem to be a lot of bugs in the code, and it's very hard to get a consistent state over multiple nodes. But of course, I guess everybody in the room agrees, open source software is very nice in this regard because we have the full sources of Nimble, so we can really go down in the detail of the Bluetooth stack and also, of course, of Riot and the network stack to make sure that where the state inconsistencies are coming from. And yeah, of course, one other problem, sniffing for BLE advertisements in this room, particularly, it's quite fun, but not really helpful. Yep. that was it. So thanks for your audience.
So SRv6. Do we have someone for presenting on this one, SRv6 mobile user plane? No? Okay. SSH. Okay, how about Swift?
SSH form.
SSH, yeah, they're at the end. Thanks.
Yeah, thank you. So welcome everybody. I'm Vincent. A few words about the Swift codec project. It deals with packet loss recovery using FEC codes for whatever codecs. The key benefits of this approach with respect to other block coding techniques like Reed-Solomon, Raptor, things like that, is to reduce the added latency. That's the key point. And of course, this work has a strong relationship with the Coding for Efficient Network Communication Research Group and also AG, as well as some work we're doing on this RLC FXC scheme at TSVWG. So the hackathon goal was twofold. First of all, we want to design open source free and reference codec for sliding window codes in order to facilitate tests and acceptation of those technologies. And the second goal is to challenge our generic API for such FEC codecs. And that's also very important to take advantage of this hackathon project to try to see problems in this internet draft. So this is only our second hackathon. We started last time, so Bangkok. I think we had great achievements because we managed to fix a few problems, mistakes, or imprecisions in this generic API internet draft. We almost finished the encoder part, which is more or less out of the work. We are still going on with tests, but basically it starts working. We also managed to do this reference demo applications in order to test this and stress the codec. We started a Python wrapper, and we also started some more or less the decoding parts. So that's great. We are very happy with that, and very happy from on my team, composed of 5 people this time. So that's great. So thank you.
Wishy. For those of you who are wondering, I skipped TLS and SSH. We're doing them at the end.
Okay, does that work for you? Yep, looks good. Thank you. Okay, this is a report from the Wishy hackathon activity. And WISI stands for Work on IoT Semantic and Hypermedia Interoperability. This work originates from a Think Research Group workshop we had 2 years ago, actually here in Prague. And we've been in these 5 hackathons so far, turning some of those great research ideas into practice. The plan, as the name implies, was to work on interoperability, and in particular using semantics and hypermedia as a tool to achieve that. There are quite a few IETF and IRTF specifications included from Core Working Group, Think Research Group, and also from W3C Web of Things group. Usually one of our goals has been to turn lights on and off in various different ways, but this time we're actually focusing a bit more on the software side. But the overarching goal has been connecting things from different ecosystems and making that happen automatically without any human involvement and using hypermedia and semantics. This time we've focused quite a bit on Coral, the new constrained RESTful application language, and how that can be used to bring IoT and hypermedia closer together. Also, we were exploring on the semantic space, what is the right level and what is the right place for expressing semantics in IoT hypermedia. And also, in particular, we're working on improving the semantic interop and resource description for Riot OS. Some of our achievements from the weekend: there is now new open source parser from text form of Coral. Still not published, but it's going to be out there soon. Also for the Riot OS, there is a basic Coral encoder and parser, and also a module for the constrained IRIs available and open source. Because everybody likes use case and examples, there's a set of those described in our Etherpad. You can find more information there. And also we're working on this translation from Web of Things thing descriptions to Coral, because those two technologies are highly related but slightly different use cases. We wanted to see how can you go from one to another. Also, there is a Python Coral implementation, which was now updated to the latest version of Coral, and also now has a nice visualization engine, so you can make Coral perhaps more human-readable in some cases. Also, there was some work on improving Resolve directly implementations, and also making the live-with-Emden TD generator that we have been using in the previous hackathons to use the latest version of thing description and be more compatible with the rest of the ecosystem. Some of the things that we learned, Coral seems to work, in particular for resource discovery that we've been using it for. These kind of hackathon activities are a very good way to get some implementation testing guidance on the technology that we are using for, in particular for Coral. And what we did manage to achieve here is get a better understanding how these things can be integrated and actually make to achieve interop in IoT. And in case you're wondering what Coral looks like, that's one view of it from the visualization engine that was hacked during this hackathon. We were about a dozen people working on this, and we're thinking probably next time we're going to need a bigger table. It was sometimes a bit hard to squeeze in everyone in the same table. Luckily, we managed to do that. And we also had 3 newcomers, so thank you everyone for joining. And if you want to have more information, there's the entry point. Just follow the links and semantics, and you'll find a lot of information. Thank you.
Okay, so Alex, we'll do yours next. Assuming, did it get uploaded? You might have to help me find it. Right here. All right. You can go forward and back here. You can use this mic.
Hey everyone. This time we work a little bit on WebRTC and RTC Web. So WebRTC and RTC Web are two sides of the same technology. WebRTC is the JavaScript API that belongs to the W3C standard committee, and RTC Web are all the protocols that belongs to us. There is still a little part of it that is not finished and is delaying a little bit the standard. And that part is about simulcast, which is the capacity to not only send several streams inside a single connection bundled, but with different resolution of the video. In our case, it's only on the sender side where we try to send different resolution. The receiving side is only receiving one of the stream depending on the bandwidth condition, and it necessitates to have a media server in the middle. So it's a very specific case where you actually not only have a browser, but you have the protocols, but you also need to have the media server people to come together. So for the first time here, we said, okay, let's have everybody around the table, the client side, so the browser vendors and the SFU developers, so we can fix the bug all together and have a real interoperability test and fix bug all together, right? So We wanted to create bugs, fix them, and generate some tests that could be run later on to make sure that there is no regression in the different test suites, the WPT for the W3C, and a new test suite called Kite that we're using to test the protocol and interoperability for the IETF part. This was the biggest hackathon for IETF. That was the biggest hackathon for the WebRTC group as well. We were 19 people, including 13 people listing only WebRTC as the reason why joining the hackathon. We had all the browser vendors actually coming and joining, developer of the WebRTC group, and so on and so forth. We had 3 of the tech lead of the media server open source in the world out of the 6 or 7 there is out there, so it was quite a success. Everybody had a different goal. The SFU vendors wanted their SFU to be the best. The browser vendors wanted the browser to be the best. But everybody has an incentive to work together, so it was beautiful. We actually fixed more than 10 bugs as of 10 a.m. this morning and filed a lot of bugs and wrote a lot of tests, so that was a very successful session. There were some really nasty bugs where instead of allowing bandwidth to be used for the high resolution, you would actually reserve bandwidth for the low resolution, which is not exactly what you would like to do intuitively. Some very, very nasty corner cases that were only found because both the server people and the browser were here. We ended up with a document showing the status of all the browsers, as well as the status of all the SFU that will allow us to make a roadmap for the next meeting until Montreal. There we go.
Okay, I have a couple remote presentations. Is there anyone else in the room who sent me a presentation that I skipped or missed? Okay, which presentation? You have to help me find it. Which one? SRV6, okay, yeah.
Hello, this is Satoru Matsushima. I'm working for the SRV6 mobile user friend project. The hackathon plan is to implement the stateless translation between the GTPU, which is one of the tunneling protocol in the 3GPP, and to the segment routing IPv6 packet. So the target of the platform is the BPP, FIDO, the project, and also the P4 in addition to that. So target function, we have actually several functions to do that. So the target will be limited to cover this limited time. We already understand the current draft, not mentioned clearly. So then through the hackathon, we are trying to figure out what are missing and what we will need to do in the future. So this is what we got done. We have the list of the function should be target, but we focus on these two, SRV6 to GTP and GTP to SRV6. So this ugly handwriting illustration is the only the guidance for our colleague. So I'm sorry for that, but our team successfully implemented this idea. Great. So thank you very much. So what we learn here is something, the coding for the SRV6 is fun to find the application inside of the segment ID, even for the other side of the standardization body. So it is possible. So mapping rule between GTPU and SRV6 has been studied. We find the some missing parameter to be configured to pick the right bits from the source port, source IP addresses, for example. To wrap up, we have Kentaro, Andre, Philippe, and Ahmed, Pablo, Chenri, and
So we'll start with
Masakada-sama from remote. All of us, I think they are the first hackathon. So the outcome is available from this URL, so you can find the code from that link. Thank you very much.
Okay, so again, it's a great pleasure to be here for the IETF 104 Hackathon. So,
so our next couple of presentations, we have two presentations being done remotely.
One slide.
Logan, are you there?
So we've been focusing mostly on implementing person-centric authentication and integrating TLS 1.3 in APIs of libraries and things like programming languages. We've been working remotely from Mauritius.
Give me feedback. Logan, can you say something now? Okay, keep talking for a few minutes because I want to see something here. Okay, can you say something now?
TLS 1.3 in
okay,
PHP 7.
Great. Okay,
Last time
perfect.
we made an initial patch. We also do changes and we reviewed them, and then it's close to getting merged. Person-centric authentication in wget
so,
and Nagios.
Which one would you like me to do first, SSH or TLS?
Really, with PHP, but it's more like the implementation is OpenSSL. TLS 1.3 coming up in Kubernetes, controller plugin.
Oh, okay.
Patch is still in. And now, how does it sound now? Okay, so next is Nmap,
yes.
Still in progress. And
so I'll advance the slides for you. Just let me know when you want to go forward.
It's been done by another guy who is on site. And then we've got one person working on Twisted in Python. Next slide, please. So what we learned, maybe OpenSSL needs to rewrite the API for person-centric authentication. Next slide, please. So the team member, then there's Kodaren, Rahul, Diresh, myself, and there's really one young guy, Kishan. And also we've got one person who's been working on, and I just mentioned this briefly. His name is Vigesh, together with a guy called Kifa. They've been working on improving their HTTP 451 module for Drupal. It's been reviewed by the Drupal developers. So we had one young person. His name is Rahul. He's been working on integrating the SCP LE PHP code point in NetPerf. And
so Logan, you are breaking up pretty bad in the room here. I don't know if there's anything you can change quickly on your end.
Only drop the patch is in, and I have a rough patch for routing advertisement in Linux. And basically, we try to touch as many working groups as possible during this IETF. And now I'm going to switch the mic to Nitin, who's going to talk about SSH.
Okay, we can see the slide here.
Okay. Hello, everybody. My name is Nitin from the Cyberstorm team. I'm currently working at
just keep talking.
Orange Business Services as DevOps engineer. So for this hackathon, we focus a lot of OC4 removal on SSH. So planning well before the hackathon was the most crucial, which includes compilation of both old and new libraries such as Ruby and Node. Can you please switch on the... So luckily we have tools such as Rake, Gem, NPM, and others. We also had to take into consideration the version of Ruby and Node running in the background and during Gravis testing and deployment. Also, unit testing, which should be compatible with OS running at VM level. Wireshark was used for pre-check and post-check and also after code deployment. As usual, we also have to debug a lot we have to debrief ourselves a lot for the IETF draft so that we can catch up with the new change which has been going on recently. So, so can you switch on the other? So OC4 today has several weaknesses. We should take into account the possibility to decrypt user sessions. Usually OC4 is ancient in cryptography. It is still widely used. During post-handshake on key exchange, we have not seen that OC4 is still being advertised, such as in NetSSH and Node. NetSSH is widely used in VMware and several Ruby intersystem.
I'll bring
Some
up those
apply
slides.
for Node as well. Can you switch? So as mentioned, there are too many deployments of SSH still shipping with OC4, and I believe we still have lots to go. I invite open source developers to support this to move forward in the future. So thanks to Red Scholar for Needful at IESG and Camara for the IETF draft.
Okay, your slides are up. Just let me know when you want to advance.
I'm going to put that is that we have Bruno Bernard who also work for the IETF mobile app working group. So we have moved on the IETF mobile app to make more improvement. We also had Jack Vielucki who worked a lot on the Node to interpret OC4. The team is now a group of 20 guys working on different working groups, all from Mauritius. We strongly believe in a rough consensus and running code, and we're looking forward for the next hackathon in the IETF team. And thanks a lot, Charles, and all the sponsors for the IETF hackathon. And we look forward for the next hackathon in Montreal. So see you. Yeah, great time with you all.
Okay, thank you very much, Nitin. And thanks to Logan, too. Okay, anyone else with a presentation? Anyone we missed? All right. Well, great. Huge thanks to everyone who did present here. If you didn't present, but you have some results you want to upload, or if you want to, re-upload your presentations, if there's some stuff you didn't put in or whatever, that's perfectly fine. It's great to have that as a resource and as a record of what happened here. Also having the recording from the MeetEcho session is great. One of the things I'm trying to think about now is a lot of you shared links to GitHub repos and various open source projects that you were working with. I think it'd be good if we thought about how to, make that easier for people to find. And so if you have some ideas about, how to make it, of course you can go to the wikis and you can sort through everything, but maybe ways we can tie the work you did back to the drafts and, just make all that easier for people to navigate. Let me know, because that's something I'm starting to think about and talking with the IESG about. Want to again, thanks everyone. I know we ran over time, but I really did want to give everyone a chance to share their results. I'm also looking for suggestions about what we change so that this event continues to go well. I assume it will continue to grow. I sure hope it does. And so we need to think about scaling it and things that work better. So I'm open to suggestions there too. Catch me now after this or anytime. I'll be around till Friday. With that, I just want to thank again Oracle Cloud Infrastructure. It was fantastic that they sponsored the hackathon this time. That really helped. This is getting more expensive because we take up more space, need more tables, need more food. We certainly could have used more beer. So if any of you have the ability to help sponsor, I welcome that. Let me know and or talk to Alyssa, and we'll figure out how to try to make that happen. But thanks to Oracle for that. And thanks to Meeteco. They did a great job. And all right, that's it from my side. Thanks everyone. Really, you guys are the ones who make this happen. So I'm glad that you take the initiative to lead projects, put them on the wiki, and spend your weekend here. So give yourselves a huge round of applause, and thanks a lot for making this such a success. All right, with that, I won't keep you anymore. Thank you.